We looked at a number of different contaminants, including chromium-6. Coming in, you can see there in the yellow triangles between 30 and 50 micrograms per liter. You do see a little bit of an acclimation period here right at the beginning while the bacteria are acclimating. But within a couple months, we saw a complete removal of that chromium-6 down to the detection limit of 0.01 micrograms per liter. Now, we did do some characterization. In that case, you're just converting Chrom-6 to Chrom-3. It's not degassing like nitrate is. And so you end up with Chrom-3 solids in your backwash wastewater, and we did characterize those. What about PCE? We didn't see any breakthrough of the PCE coming in from the system, and we were spiking it all the way up to about 500 micrograms per liter. These are GAC-based systems, so of course there's a concern that you're just getting absorption. At the end of the year, we took off all that, took that carbon out, and did the leaching procedure tests on it. We found that only 6% of the PCE that we were dosing to the system showed up as being absorbed to that carbon. Look for all the daughter products, TCE, DCE, vinyl chloride, did not have any of those show up in the system. Same thing with TCP, trichloropropane. High concentration coming in up to 400 micrograms per liter. You can see a partial removal in the first part of the first stage bioreactor, and then the rest of that was removed in the second stage bioreactor. What about DBP formation potential? You are adding acetic acid. It will form DBPs if it goes through your system. This was a series of 3 DBP formation potential tests that we did from the BIOTTTA system, where we took raw water, we took effluent from the first stage bioreactor and effluent from the second stage biofilter, dosed it with chlorine at a very high residual of around 5 milligrams per liter, left it in the trailer for 7 days at about 90 degrees. And you can see the formation potential here, even out of that first stage bioreactor, was quite low. Important, and this has been emphasized a few times, the importance of being able to control your dose of acetic acid so that you're not overdosing, you avoid ending up with any DBP formation potential. We've done a lot of the molecular microbial work on these systems for a couple reasons. One, we want to see what the shifts in population look like as we change operating conditions. Helps us determine if we are missing a nutrient or if we have the community there that we need. It also helps us understand what we might need to do from a disinfection perspective. In these studies, we found that the vast majority of the bacteria are from the beta subgroup of the proteobacteria, and that's important because they're all gram-negative. These bacteria have very thin cell walls and can be inactivated very, very easily. Did the CT, or the disinfection tests with free chlorine, and CTs as low as 2 milligrams minute per liter. Decreased the HBCs coming out of the system, which were greater than 5,700 CFU per mil down to less than 100 CFU per mil. Turbidity, very important. We've got to meet 0.3 NTU. And as I mentioned, we had a little bit of polymer coming out of that first stage bioreactor. You see the red peaks here. That's the turbidity coming out of the bioreactor. Every time it does a backwash, it does produce a little excess turbidity. But as long as we condition that water a little bit and apply it to our biofiltration process, we see very low turbidity coming out of the effluent, even handling all of the peaks of turbidity coming out of the bioreactor. What about the waste production from these? Recoveries in general are about 96%, and it all depends on what you want to do. If you don't want to recover any of the solids out of your backwash waste, you'll end up with recoveries around 95, 96%. If you want to increase your recovery, squeeze a little bit more water, produced water out of the raw water, you can settle those solids, return that water to the head of the plant, and get more high recovery. What we found in terms of the quality of the backwash wastewater is, as we expected, it's mostly consisting of volatile suspended solids, or these cells that make up your biofilm. About 200 to 300 milligram per liter is about what we see on average, a composite sample of our backwash water. And that exerts a chemical oxygen demand of about 200 to 300 milligrams per liter. And that's important because at least in Southern California, you get charged for, in some places, charged to deliver a waste to your sewer based on volume, based on VSS, and based on COD. Head loss in these systems tend to be very low. We'll see what it's like in a system that's treating 170 milligrams per liter of nitrate coming up. But typically what we see across the entire system is about 20 to 40 feet of head loss. Very important from a pumping and an O&M cost perspective. Implementation. One of the things that's a little bit different about BIOTTTA is that it's a completely packaged system. It's not just a biological process. It's that full treatment system. Control volume looks like this, where you've got not just a bioreactor, not just the reoxygenation step, but also the biofilter on the back half. It absolutely is the tail that wags the dog in terms of overall treatment. And what we found is that it's important to integrate the entire process. There's no post-treatment downstream of the BIOTTTA system itself. And what you end up with is a system that's skid mounted, and I'll talk a little bit about that. It's very simple to operate. The controls for the entire process, bioreactor through the filtration step, are all integrated. Footprint can be very compact. The robustness, I showed a little bit of that earlier. The fixed bed system tends to be very robust. It's scalable and very flexible in terms of contaminant loading and types of contaminants. It's a modular system. This is an example of a skid that we've designed for 400 GPM system in Minnesota. Those are 8-foot diameter pressure vessels, and that's the full treatment process that you're looking at, with the first stage bioreactor, interstage degas, along with the polishing biofilter, PLC and controls right here. These are all standardized, and basically what it ends up with, we have kind of a menu of skid type systems from 4-foot diameter pressure vessels up to 14 feet. Up to 8 feet is what's skid mounted. Beyond that, it doesn't make sense to put it on a skid. The systems, again, the control on the system is all integrated with the inline analyzers, and there's remote monitoring, alarming, and control available. The modularity of the process simplifies sizing per site. This is a site that we looked at actually in the Central Valley of sizing a system at about 400 or 450 GPM. You get a feel for the size of the vessels there. And again, it's the package system and the ability to look at treatment not just for your target contaminants, but also all the way through meeting all the surface water treatment requirements, turbidity and disinfection and so forth, putting it all into a single system. What that allows us to do is really keep this and work together with system fabricators, allows us to keep very consistent control. Standardization on the equipment allows us to do that. And from a delivery perspective as well, it can be done a number of ways. You end up with a system, it's fabricated, it can be design build, can have full service options if that's needed for startup, for technical support throughout a project, electronic O&M manuals. It's really a full service package, start to finish. What about costs? We've heard a little bit about this. System capacity really drives costs. Your raw water nitrate, at least in the typical ranges that we talk about, and your treatment objectives don't really drive the capital costs very much. We see our sizing really is just driven by how much water you need to push through that. Again, I'll find out if that's the case for a system that has treating almost 200 milligrams per liter of nitrate. O&M costs are driven largely by water quality. Chemical costs drive O&M costs, and your nitrate, the amount of nitrate you're removing, combined with the unit cost of acetic acid, really drive O&M costs. As you've heard from the other speakers today, we're looking at a 50 GPM system that's operating 24/7. Put that into a model that we've also developed over the last few years that sort of sizes the right skid, the pressure vessel size, and what we ended up with was one 2-stage skid with 4-foot diameter pressure vessels with all the control system in the inline analyzers and the backwash system. It's got a 60 milligram per liter raw water nitrate concentration, and we're going to treat that down to about 30 milligrams per liter. We've developed out of that a cost model as well, and the cost model right now is actually built on real costs for an 8-foot diameter pressure vessel system. So we've had to do some scaling to get down to a system that's smaller, this 4-foot diameter pressure vessel system. And this is where we end up, and it's been kind of interesting to see the cost ranges seem to be fairly similar across the board today. The equipment costs, again, everything inside that control volume, about $200,000. And the annual O&M somewhere just under $10,000, most of that being chemicals. About $6,000 of that is your chemical cost. A couple thousand of that is the power cost. So again, it's kind of a novel approach to thinking about groundwater treatment, targeting the avoidance of add-on technologies and post-treatment processing, which may be variable or unknown, trying to put the whole thing into a package together that makes it very efficient, hopefully very cost-effective. We believe it will be very cost-effective and very robust at the end of the day. Question?
There's a question at the back of the room. While you go up there, I have a question.
Yes.
While we're focusing on nitrates, in the town of Hinckley, one of the, I guess they use ethanol, and one of the byproducts has been manganese. Is that something that you found?
Manganese?
Yes. Is that something that you found as a byproduct of your process?
No, we've not seen manganese as a byproduct of this process. A number of, there are some typical surface water treatment chemicals that do end up with some manganese, producing some manganese through the process, but we have not seen manganese production.
Okay. Okay. Go ahead, sir.
Garrett Walker again, City of Angels Camp. Just a question about your peroxide. You're saying you used peroxide as a reoxidizing agent. How much are you using on that? Because I know O&M costs on peroxide's relatively expensive in comparison to some other chemicals.
So typically, when you add a part of hydrogen peroxide, you end up with about a half a part of dissolved oxygen, depending on how it's added. So we're looking to keep the effluent of these systems above 4 or 5 milligrams per liter of DO. So 10 milligrams per liter is our typical, 10, 12 milligrams per liter is our typical dose. Again, there's multiple reasons. You're right. It's not as cheap as just aerating, but it also gives you some advantages in certain scenarios. Keeps everything in line when you aerate the water. If there's anything that's volatile, hydrogen sulfide, VOCs, you have to worry about capturing that. We also use the hydrogen peroxide as a biomass control agent. Found it to be extremely effective. And if there's one thing I've learned in the last 15 years on this system, the hydraulics of a biological process, in particular fixed bed process, cannot be, you cannot put enough emphasis on maintaining good hydraulics with your backwash and whatever biomass control systems you have.
Other questions? Center there, Chris.
I guess to follow up on that last one, do you have any analyzer to measure the residuals or anything of the peroxide?
You can. I don't know of an inline analyzer. There are tests that can run, basically weight chemistry tests that you can run to measure peroxide, but we do not. When we run our biofiltration systems on surface water with peroxide, we are measuring peroxide through our biofilters. We don't see any peroxide in the effluent. That peroxide will react to form oxygen first. If there's any left, it's going to be quenched by that GAC that we use. In fact, it's one of the GAC is one of the quenching techniques that you can use for an advanced oxidation process system.
I see no more questions, so thank you. Home stretch. So this is our last presentation of the day before we go to audience questions. And I'm hoping that some of the presenters from today are still around in case you have something for a particular person. And depending on the number of questions, that's when we get out of here. But I do want to encourage questions. Thank you. I don't know how to say your last name, so please introduce yourself. I can. Isam Najm?
Perfect.
There you go.
Thank you.
Thank you.
Well, I very much appreciate you staying here till the end of the day. I hope we will keep it interesting for you and make it worth your while. My name is Isam Najm. I'm with Water Quality and Treatment Solutions, an environmental firm in Southern California. Let me tell you a little bit about the outline of what I'm going to talk about, a brief introduction that I want to make sure I tell you about, the configuration of the biological denitrification system that we evaluated, the performance, and then comparison of alternatives. I think I want to circle it back to the fact that this is mostly a discussion about small systems, and Eugene gave us alternatives that he wanted us to evaluate from a cost perspective, and so I'm going to focus on those two alternatives, and then a general set of observations at the end for what it's worth. First, I want to tell you that the information that I'm presenting today is a product of two demonstration studies that we did, one for the city of Glendale in Southern California, and the second is one that was jointly funded by LA County Department of Public Works and the Water Research Foundation, and they provided the full financial support, these three organizations, for these studies. And obviously, if any of you know me, these opinions in here are mine, and I cannot claim them to be those of the funding agencies. One clarification that I want to also put out: we are not a technology provider. We are an environmental engineering and science consulting firm. So what we do is evaluate treatment options for water agencies, and we have no vested interest in any specific technology, and frankly, I don't care what technology someone picks as long as it's the best technology for that application. And so the reason I'm here is simply because we conducted the study on biological treatment for the city of Glendale, and we received the letter of conditional approval of the process that we tested along with the city of Glendale, and Eugene asked me to be here and talk about that. So let me tell you a little bit about the configuration of the system that we used, which is similar to what Jess Brown mentioned earlier from Carollo Engineers. The introductory slide is always a good cartoon, and so let me go through it quickly because I want to emphasize something that has also been mentioned here today. The idea is to use natural bacteria to consume the oxygen and the nitrate in a water. And it does that by adding acetic acid, which is basically vinegar, as well as a phosphate, which is a nutrient. At the phosphate dose is roughly about 0.2 milligrams per liter, so it's a fairly low dose. That's ASP. So with those additives, the bacteria are able to convert the nitrate to nitrogen gas and generate more bacteria. And really those two products is what the entire treatment system pretty much is all about. It's about handling those two products of the biological process. So I want to spend some time on those products for what it's worth. So if you look at the overall treatment system, we utilize a downflow pressure vessel system that has activated carbon in it. This is a standard filtration process that people use for all kinds of applications. It's basically a pressure vessel. The water comes in with the high nitrate, acetic acid and phosphate are added and goes down through the bed of the filter, and that pretty much does the biological job. What we have in this product water, we have low nitrate, which is the goal, but we also have low oxygen, we have excess nitrogen gas, and we have high bacterial counts. And so the rest of the discussion becomes about these other things that we don't want in that product water. And so these three things are what dictate what happens downstream from this biological process. So first we go through an aeration process, and the idea is to take the water up and bubble air through it to simply strip out, predominantly to add oxygen, but also to strip out the nitrogen, the excess nitrogen that was the product of biological process. So with that, we get rid of two of the three problems that we had before, but we still have the high bacterial count coming out of this at this step, and that's why DPH requires the subsequent steps of filtration and disinfection. And so we look there at another pressure filter vessel with a coagulant addition, and followed by a disinfection step. Both of these aim at addressing the high bacterial counts that are coming off of the aeration process. And so it's only at that point that we're able to achieve the goal of the low nitrate plus replenishing the oxygen, removing the excess nitrogen, and addressing the high bacterial counts that are in the water. Is aeration necessary? And we've heard talks about how different ways to oxygenate. I believe that aeration is necessary, especially for a system that needs to be in a continuous operation. If a system needs to run for a few hours and then shut down for the day, like some small systems do, you can probably do it without aeration by adding the hydrogen peroxide approach that Jess mentioned. In my opinion, a continuous operation does need the aeration step because the nitrogen gas becomes a problem for the filtration process downstream. And it becomes a battle between having a water that has excess gas and a filter that you're trying to operate to maintain good turbidity removal. So in my opinion, aeration is a necessary step. For short intermittent operation, as I mentioned, you can use an alternative approach instead of aeration, like a hydrogen peroxide approach. A little bit about the performance of the biological process. This is some of the data that we generated from a study that we just completed. This is for LA County Department of Public Works. And we operated the pilot unit for 4 months. And the green circles are the influent nitrate. They're just below the MCL of 45. And the blue diamonds, what you see, is the effluent nitrate coming out of the entire treatment system. And the control system was set up to maintain nitrate between about 5 and 9, which is really 1 to 2 milligrams per liter as nitrogen. And that was intentionally done to maintain good aesthetic quality of the water coming out of the system. The last thing you see at the end here, this spike here, this was actually one of those challenge tests that DPH requires as part of the testing process. And the idea there is to shut down the acetic acid system, assume that it failed, and what you're going to do. And so what happens over the next 24 hours until somebody notices that the acetic acid is not being fed. So that spike is the response of the system to the loss of acetic acid. So maintaining proper chemical feed is a critical component of a biological treatment system. Bacterial levels can be tremendous. The point of this is to grow bacteria to do the job. And so then at the tail end of it, we want none of them present in the drinking water. And so this is a profile of the typical bacteria, HBC counts that we measure, but also the total coliforms. There was no E. coli at any point in the treatment train, which is good news. However, you do get quite a bit of coliform growth. On the biological contactor coming out of it, we had about 500 coliform counts, so it's a significant number. Coming out of the filter, there was all non-detect except one sample was 60 during an operational upset, so this is an average of that range. And it's only after you go through disinfection that you get the levels that you'd like to have in a drinking water supply. And so it's important to recognize the importance of everything other than just nitrate removal to produce potable water quality. We heard about chromium removal. This is also some of the results from the study looking at Chrome 6 removal. The water was actually spiked with Chrome 6. It did not have it, but it was part of the evaluation. And the influent was about 25 micrograms per liter, and the effluent was in the 2 to 4 microgram per liter range. So it's a fairly effective process at removing it. But it's important to recognize that while nitrate is destroyed to nitrogen gas, Chrome 6 is simply transformed to Chrome 3. And so all of it is still in the waste backwash water that is produced from the system, and all of it will be disposed of as part of the residual stream. So chromium is not destroyed, it's simply changed form and concentrated into the waste backwash water. And that's important to recognize once you start talking about what you're going to do with that waste wash water. This is Eugene asked us to give some information on the quality of the backwash water. This is the quality of the backwash water out of the Glendale pilot study. And you can see the nitrate levels, sulfide, volatile suspended solids, similar levels that Jess mentioned. And to put this in perspective, this is obviously a lot better quality for sewer discharge than any residential waste discharge. And so from that perspective, it's a great process to produce a residual that can go into a municipal wastewater system. Can the waste backwash water be recovered? Can we capture it and recycle it? And I will tell you that the Glendale pilot study that we did not recycle the backwash water. We simply discharged it to the sewer. The study that was done for LA County was done in a septic area. So one of the biggest questions was how much can we minimize the discharge of that waste product? And so we did include recycling of that recovered wash water back into the system. And I can tell you that, yes, it works from an operational perspective, but it is fraught with complexity and it's fraught with pitfalls, because smallest hiccup on a return wash water system can cause aesthetic quality problems in the drinking water that's produced by the treatment system. What I mean by that is you are taking the waste backwash water and you're concentrating the sludge and then recovering the water on top. If you don't manage that sludge properly, that sludge would turn septic very quickly, and it'll cause aesthetic problems. It'll release organics into the return wash water. It's a different animal than just say straight through treatment, then take waste backwash water and dispose that. And so in my perspective, a small water system has enough problems to even attempt to do that. And so I would not recommend utilizing a return wash water system for a small water system application because of all these issues that I mentioned. Online monitoring. I know you heard a lot about, there's monitoring for this and monitoring for that. And it's very true. We use monitoring for nitrate, turbidity, chlorine, and oxygen. But you got to remember that these are very costly instruments. Just a ballpark number for these is about $25,000, and that's just to buy them. So now we have instruments that are highly technologically advanced instruments that we're asking a small water system to maintain and make sure they're operating properly. I don't think that's a very viable option for many applications. And so I would ask how important it is that we have all of these instruments. What can we live with to make potable water with as little or as few of these instruments as possible? And I think we need to address that at some point. Comparison of alternatives. I want to go a little beyond what was mentioned earlier. Eugene actually asked us two alternatives. He asked us for a small system that produces 72,000 gallons per day. Basically a system that either runs at 50 GPM 24 hours a day, or a well that runs at 125 GPM 10 hours per day and then shuts down for the rest of the day. So basically a system that takes water out of a well, pumps it into a tank, the tank is full, in 10 hours you're done. And then you come back the next day. So we evaluated both of these systems for this discussion today. So if you look at the characteristics of a 50 GPM 24-hour system, this would be a smaller system because you're not treating 125 GPM capacity, you're treating only at 50 GPM capacity. But its continuous operation, in my opinion, does require aeration to remove the excess nitrogen. On the alternative 2, which is 125 GPM for only part of the day, it's a larger system that requires larger vessels. So it's going to have a higher capital cost from the equipment perspective. However, I would say that the jury is out as to whether this short-term operation and then off would actually require aeration. It probably can operate with an inline injection of, say, of hydrogen peroxide if it's economically viable. And so in that sense, that is an open question right now for an intermittent operating system. So I want to emphasize the complexity of this overall process. This is the existing system, a well pumping into a tank, chlorine addition. Nothing is simpler than this. So anything we put on here is going to be more complicated, more expensive, more scary. So if I look at a 50 GPM 24-hour per day system, this is the treatment train. So we're going through the first biological vessel, an aeration process, and a filtration process with acetic acid, phosphoric acid, coagulant, and chlorine addition. 4 chemical feed systems that we're putting in this system. And that is only for the treatment train. Now we have to talk about the backwash system. We need backwash pumps to take water out of the clear well and backwash the vessels. And now we have a waste backwash system. So we've got to take that waste backwasher and put it in a waste backwash water tank and then dispose of it whichever way we need to dispose of it. This is a lot more complex picture than the picture that I started with before. And I can't emphasize more how important it is to recognize that when it comes to this versus other systems, this is not a simple system. It's a complex system. The good thing about it is that in many instances, it provides a solution to a fatal flaw of the other systems, which is producing the salt brine that we don't know how to deal with. So it provides that relief from that fatal flaw because it generates a waste stream that is manageable. But make no mistake, it is not a simple system. It is more complicated than the existing conventional systems, which have developed through years of maturity to products that are out there on the market. So that's my personal opinion of this. And this is the configuration of the second alternative. So the cost assumptions, and Gene asked us for cost, so I'm going to put out the cost assumptions and then present the cost that we developed for them. These are the characteristics of the system. Daily production of 72,000 gallons, nitrate in the groundwater of 60. I'm not sure where the target 30 came from, but I assumed that you're treating the full 50, not partial flow. So we have two alternatives, and Eugene suggested that we use a cost multiplier, so evaluate the equipment cost, then multiply it by 2.5 to develop that would be the total cost. I am assuming that this space is available to install a treatment system. In other words, you don't need to acquire additional land to install the system. And I am also assuming that there is an availability to dispose of the waste backwash water. And let's assume it's a septic system for now. So that septic system needs to take the waste backwash water out of this treatment train. And I think I want to talk about that a little later here. These are the general characteristics. What the empty bed contact time, the size of the system. The number of backwashes and frequency of backwashing is very critical to decide how much waste you're going to generate. You can be down a 24-hour operation or 48-hour operation depending on a lot of factors. And this is a case-specific issue. The more nitrate you have, the more frequently you have to backwash because you're generating a lot more biomass. And so that's a complicating factor in the overall calculations. So when I put all that together, and I don't know, I hope you can read the numbers in this. So with the assumption that I mentioned earlier, we estimate the equipment cost by itself under alternative 1, which is the 50 GPM system, to see somewhere between 200 and 250. And the alternative 2, the slightly larger system, even though we don't have the aeration, the increase in the size of the vessels and the increase in the waste backwash water tank, because now every time you backwash, you produce more water because it's a larger vessel. It's 250 to 300,000. If I use the cost factor multiplier of 2.5, you're looking at 500 to 625,000 for the smaller system and maybe slightly higher as a range for the larger system. Chemical costs, I estimate them to be quite a bit higher than we heard before. I estimate between 20 to 25,000, and mainly because we really don't know what is the cost of acetic acid delivered in small volumes to a rural community. There is no information on that. We have cost information on acetic acid delivery to a metropolitan area. We know it in small volumes and large volumes, but I cannot tell you how much it would cost to buy a gallon of acetic acid and have it transported 4-hour drive in a 55-gallon drum. Those 55 gallons are going to be pretty pricey. So I'm estimating that the cost of chemicals is going to be higher than for a urban, larger system setting. But what I want to emphasize is this point down here. If you were to choose between the two, I think it's important to recognize the wastage rate. Now, I say for the smaller alternative, up to 8,500 gallons per day. That's because if you backwash once a day or you backwash every 2 days, that volume changes dramatically. But if you go to the larger system, the alternative 2, you would be wasting double the amount of water. And the reason is, when you have a larger vessel, it takes more water to backwash it than it would a smaller vessel. So if I run it for 10 hours and stop, I'm producing the same amount of water, 72,000 gallons in a day, but I'm using more water to backwash it. So I end up with about 20% wastage rate. It takes 20% if you backwash every day. It takes 20% of the water that you treated to backwash the vessels the two vessels on the biological process and the filter in my calculations. And so for that reason, it's a lot more palatable to go to a smaller system. Even if the costs were the same, I think the waste volume and what to do with waste volume really becomes the parameter that makes the decision for you in an application like this. And so from my perspective, I totally agree that biological treatment is highly effective at removing nitrate, Chromium-6, and you've heard about other contaminants. It does generate a waste stream that can be discharged to any septic system because of the quality of it is not different from typical wastewater that a septic system would take. But I would argue that it is quite a bit more complex and costly than other systems such as ion exchange. If there's no fatal flaw for the ion exchange process, and I guess we'll hear tomorrow about maybe some options for overcoming that fatal flaw. But that is really the biggest issue here. So I can tell you that all the large systems that are looking at biological treatment are struggling with how they're going to implement it and how they're going to operate it, what's it going to take and what's it going to require of them. So the idea of going straight to a very small system and putting it in and expect it to work as we're talking about, I think it's a bit of a stretch at this point in the game. It's just my opinion. And the higher wastage rate, I think, is that going to drive the sizing and operation of the system. It is better to design a smaller system that runs continuously than it is to design a larger system that runs intermittently, even just on the basis of the wastage rate from the treatment system. And again, I would say that wash water recovery is viable and it's great and it can reduce the wastage rate to less than 1% of the water produced. But it takes expertise and it takes careful operation and it takes someone on site to be keeping an eye on things, and I don't think it is a viable option for small solid water systems. So if biological treatment is to be applied, I would say that that waste backwash water needs to be disposed of as is and not concentrated. And that's my story. Thank you.
Okay, questions? I see one there, and we've got a microphone coming to you.
Thanks. Jim Gesselbrecht, Waterworks Engineers. Isam, your point is very well taken about the complexity. And just to follow up on that, has there been any discussion about, for this 50 GPM scenario that's been discussed, what level of certification would be required of the operator that's running this plant?
Talk about passing the buck.
Yeah, that's...
Eugene Long with Department of Public Health. I think the certification is an issue we're working with right now because this is very unique treatment that we haven't dealt with. Currently, a minimum will be T2, but it depends on the capacity of the plant. It may go up to be a T3. So we're still working on that right now because existing regulations do not address biological treatment. Thank you.
I'm Rebecca Chu with the LA Regional Board. You mentioned that the backwash water can be discharged to any septic system, but we do have a concern in our region that we deny some of the project because of their concentration in the backwash water. So don't assume that you will be able to discharge to any septic systems. You better consult with the regional board.
Well warned.
I very much thank you for that comment. I should never say anything with absolute. So I appreciate that. They should not have said any water, any septic system. I agree and I appreciate it.
Alan Miller with the Region 6. Did you only look at fixed bed reactors for your second stage? Because we've heard some presentations here about those that don't require back flushing and those sorts of things, and you said you're not tied to any particular technology, but was that what you were asked to look at?
No.
ALSA or something?
There was an initial assessment of which approach to take, but for the testing, we just tested the downflow fixed bed process.
Thank you.
Other questions? Any from the web? No? Thank you. I do have a question for Jess Brown, though. It came in. So I'll bring you a microphone. So the question is, what molecular biological methods were used to identify the microbial community? And secondly, what was the result of the microbial community shown qualitative?
So the method that was used for the plot shown was a clone library analysis. It's just basically extracting, amplifying DNA, sequencing it, and then comparing it against a database. And what you saw there was actually a relative quantitation. It's not actual numbers. It's based on the community as a whole, what percentage of the population is made up of a certain genus. We also now are more into the pyrosequencing microbiological analyses. It's a little bit more robust, gives us a little bit more information than the clone library. It was quantitative. It was actual specific genera of bacteria, just what relative abundance they were in the community.
Other questions of any of our presenters today? Okay, got a couple of hands. Is there a runner? Great.
Kathy Swanson with Siemens Water. I think you guys said at the end of this you're going to put together an apples-to-apples comparison. I think that waste rate that Isam had talked about would be really interesting as part of that comparison.
Thank you.
I was hoping for, this is Chad Seidel with Jacobs, hoping for a little bit more context for the systems that are struggling with non-compliance with nitrate treatment. Eugene, you gave the example that the folks that presented this afternoon should address, you know, this 72,000 gallons of water production per day, either continuous or intermittent operation. I'm curious if you were to describe the typical water supply for communities that are struggling with nitrate compliance, if they fall into that picture, and if they have septic versus local sewer options, and what operator attention they have currently. You know, that context might help all of us in the audience of understanding how the systems that we're hearing about might be able to be plugged in those cases.
Thank you, Chad. I think for the water systems that we're talking about, for the small system, most of them actually won't even have the storage tank that's been described in Isam's presentation. Most of them will be just a well in the ground, probably around 125 gallons per minute or even a bigger pump, because they probably sized it for fire flow. And the water would just strictly be coming up. It has a chlorine injector and goes into a couple of hydropneumatic tanks. So pretty much the systems will be cycling very frequently throughout the day, just to meet the system demand in the morning when everybody wakes up, and in the evening when everybody comes home. The rest of the day probably would just be sitting there and not doing a lot. So that's why for the biological treatment that we talk about on the large water system that we worked up to this point is based on really large cities where they can turn other wells on and off, and then allow the biological treatment system to work on a continuous basis. And we feel that that's probably where it fits really well. So for these really small systems, they probably, with just a simple chlorinator, they don't have an operator that will be on site. They may be visiting maybe once or twice a week, just to make sure there's sufficient chlorine solution that's in the chemical storage tank, so that the chlorinator won't run dry. And then they will come through the system, taking regular bacteriological samples maybe once a month. So these are really remote, very small system, and then they're not used to having an operator on site. So from switching from something very simple with a chlorination system to something like this, a biological treatment system, having it running on steady state, probably my opinion, my personal opinion, not of the department, will be probably you have a high chance of it working well because it's steady state, and then you add a whole layer of complexity into it when we try to operate in an intermittent manner, because with the small system sitting under the sun, you could be exposed to really cold temperature and really hot temperature. so it may actually affect the performance throughout the year as well. So with that, which is a very good handoff, that's why we're working with UC Davis and with the regional board in Central Valley on working on a proposal to work with these biological vendors to hopefully to test these systems to find out the boundary conditions, whether we can operate them on in some sort of an intermittent manner so they can work well, or maybe as part of the funding project that will include putting in a bigger storage tank so that they can put in a small well and allow the system to operate all the time so that they can work well as designed.
Yes, Mina Spires from City of Vacaville. It's actually for everybody to, it's for the table that you're gonna do for tomorrow is to compare if there's a limit, an upper limit for the influent nitrate levels. Because you kind of standardized 60 milligrams for every single one. I was wondering if there's an actual, like, really high level nitrates that they cannot take for individual companies.
I think for the biological treatment processes, from the work that they have done, the influent concentration could be quite high. And there's even biological treatment process studies that have been done for using the treatment of ion exchange brine using biological process. So it is, in theory, can handle really high nitrate concentration. But I think in the handout packet that was given out, there's a really good summary table that talks about whether there is the limit and design considerations for the system. And I encourage you to refer to that.
Other questions? I know it's been a really long day, but a very interesting one. And there'll be more tomorrow. The presentations can be found. Let me make sure I say it properly.
Is it on here?
Can we? So the presentations can be found at drinc.ca.gov/DNN. And we will try and post that. D as in David, N. And then go to full agenda, and you will find all the presentations. And then I believe one of them, Dr. Cones, will be later today. Oh, okay, thank you. So check the handout, it should be there. With that, I want to thank all of you for your rapt attention today. We will be back here tomorrow morning for another full day of other presentations. We will begin promptly at 9 a.m. and we'll see you all then. Thank you. If you're not coming back tomorrow, please fill out the evaluation form that's at the back of the room. Thank you.